in particular way.
Okay, thanks. So I'll be talking about a recent paper that we put on the archive last week, I think, together with Neil and Alex. And it's not going to be too long of a talk, I think, so feel free to ask any questions you might have when they come up, because we'll have plenty of time, I think. Okay, so, well, the title sort of says it all, but to summarize it a little bit more, in this talk, we are discussing the circuit extraction problem. So this is where you're given as an input a ZX diagram with the promise that this diagram implements a unitary. And then you should be outputting a description of a quantum circuit which implements the same unitary. We request this promise of unitarity because, of course, if the diagram isn't unitary, then there is no quantum circuit that will implement it because all quantum circuits are unitary. And it turns out that this problem, where we are allowed to put in any ZX diagram as unitary, is sharp-P hard. I'm going to explain a bit later what sharp-P exactly means, but yeah, it means it is very hard. It's like at least as hard as strong quantum circuit simulation. So that means that extracting a circuit from a ZX diagram is in fact just as hard as computing properties of the diagram directly, because that's like what simulating or like calculating the diagram is. Okay, so I'm going to make this a bit more formal, what's on this slide. But first, some motivation for why we're talking about circuit extraction. So suppose we want to use ZX diagrams as a ZX calculus for circuit optimization. And what we first do is you write a circuit as a ZX diagram, which is quite straightforward. And then we simplify the diagram with whatever strategy you want. For instance, we get this thing on the right here, which like is some kind of graph-like diagram from one of our other papers. But then the thing, if you actually want to use this as a circuit optimization strategy, you need to turn this diagram back into a circuit. And this is like what we call circuit extraction, transforming this diagram back into a circuit. More generally, what we're interested in is making the ZX diagram into something which can be run on a quantum computer. And so it can be a circuit. You might also think it can be like something else. And I'll discuss a little bit about that later on. But first, let's just assume that the output we actually want is a quantum circuit so that we can then run it on a quantum computer. Okay. So there's a bunch of techniques that are known to do this, to take a diagram and translate it into a quantum circuit. The first paper to do this was this top one, the graph theoretic simplification of quantum circuits with ZX calculus. And this says that if the diagram has a property called G-flow, which stands for generalized flow, then you can extract a circuit. Then there is another paper there, back again, circuit extraction tail, which says that if the diagram has extended G-flow, so this is a more general property, they can also extract the circuit. And then this last paper relating measurement patterns to circuits via Pauli flow says that if the diagram has something called Pauli flow, which is again a generalized version of extended G-flow, they can extract the circuit. Now, all these three papers, well, what they have in common is that these kinds of flows are sort of promises on the local structure of a diagram. So it says that, so when you look at like a small part of the diagram, it has to be like well behaved enough, like it prevents the diagram from becoming too wild. And this is what allows us to actually extract a circuit from it. Okay, so and so then the question is, okay, do we need such a local promise? Like, would a global promise that the entire diagram is unitary be enough? Okay, so let's formulate what the actual formal problem is that we're trying to solve here. So I define this problem of circuit extraction, where the input is a ZX diagram D, which has n inputs and outputs. So we need the same number of inputs and outputs because we're interested in being unitary. And it has k wires and spiders, so just a number. And we fix some sets G, some gate sets of unitary gates, which act on a bounded number of qubits. So G could, for instance, be the Clifford-Presti gate set, or any enumerable set of gates. I think it doesn't really matter if it's a finite set of gates or not. And then we have a promise on this diagram. The promise is that this unitary, that the diagram is proportional to a unitary. So we don't require it to be exactly a unitary, but just that up to a non-zero scalar, it is unitary. And then the output should be a Pauli-sized circuit. So this is polynomial in the two parameters we have. So polynomial in the number of qubits n, and polynomial in the size of the diagram k. And so it's a circuit which is expressed as a sequence of gates from this given gate set G, such that this circuit is expressing a unitary which is proportional to the unitary of the diagram. So that should be the output if such a circuit exists. And if it doesn't exist, like maybe the gate set we've fixed can't actually represent this unitary, then it should say, well, such a unitary doesn't exist. Okay, so I think this is like the sort of most general version of like exact circuit extraction that you might want. And if we go to these three methods, these all fit into this thing. So they take in a diagram and they output a circuit over a given gate set in this way. There are a problem of things that you might object to. For instance, this thing that it has to be a poly-size circuit. But we are sort of interested in efficient procedure to do this. And if it's not even a poly-size circuit, then just writing the output would already take too much time. So we want it to be a poly-size circuit, just so that it could be efficient in principle. The other things you might object to, like we don't allow ancilla here, for instance. We don't allow approximate synthesis, but we'll discuss those variants a bit later. But for now, I think this is like a reasonable definition of circuit abstraction. Are there any questions about this definition?
And then you think that the gate set wouldn't matter, right? So for any gate set, the problem would be the same.
So if your gate set is not universal, then there might be unitaries which you can't express. So the problem might, like say I have like an empty gate set, right? Then I can just always output no such circuit exists.
Yeah, but not that extreme cases, right?
Mm-hmm. Yeah, so generally we'll be interested in cases where G is at least approximately universal.
Okay.
Okay, then let me continue. Yeah, so first is an observation. If we weaken the condition on the circuit being polynomial size, then there is like a sort of very naive solution to this, which is just to calculate the matrix of the Z diagram, which takes exponential time, and then synthesize a circuit directly from it using your favorite exact synthesis algorithm. There's, for instance, a synthesis algorithm for Clifford-Bastille, which takes in a diagram of a matrix and then outputs a Clifford-Bastille circuit. But this generally will be an exponentially sized circuit. But this is a way to get some circuit out of your ZX diagram. Obviously, this is not very nice. It takes exponential time and generally results in an exponentially sized circuit as well. Okay, so before I say a bit more, let me give some background on complexity theory. Maybe for the computer scientists is all known, but like for myself, my background is not computer science, so some of this was like new for me, learning like when we were writing this paper. So I'm just gonna cover it a little bit. So we have this complexity class called P, which are just which we see intuitively as the efficient problems. So there's a decision problem solvable in polynomial time by deterministic Turing machines. Decision problem here means that we just output like like a true or false, which like is this thing like an instance or problem or not. And NP is like defined very similarly, but now we allow a non-deterministic Turing machine, which means that at every step of the way, we can sort of non-deterministically make a choice, which allows us to explore sort of an exponential number of paths, which means like it's way more powerful to do things, or at least we think it's way more powerful. And yeah, there's this notion of Cook reduction, which is relevant for us. So suppose we have some decision problems X and Z, like I'm not saying in which complexity class these lie. Then we say that X Cook reduces to Z when there is a deterministic Turing machine which can query an oracle for Z such that this Turing machine solves X. Okay, so we have sort of a machine, but this machine can also in constant time solve problems of Z. And then this can solve X. So this means that X is like simpler than Z, because if we have access to something that can solve Z, we can solve X. And in symbols, we would write X in P to the Z, because we have a polynomial time Turing machine with a Z oracle. So an oracle, you write like this like superscript notation. Okay, so more things we need to know. So we have an NP complete problem, which is set which stands for satisfiability, where we are given a Boolean formula and we are asked whether it has a satisfying assignment. Okay, so just is there a solution to this Boolean formula? There is a complexity class sharp p, so I call it sharp p. Sometimes people also call it number p, which is the counting version of NP. So that means that we're given a non-deterministic Turing machine, and then we need to count how many accepting branches it has. So like we are going down every possible path in the Turing machine, and some of the ends, and at the end of this thing, some of them will say, yes, this is a satisfying solution, and others will say, no, it's not. And then we're asked, okay, how many of these branches actually accept? So then the output is not whether there is a solution, but how many solutions there are. So a sort of important technical distinction is P and NP are sort of these decision complexity classes, while sharp P is more of a functional complexity class. So the output is not just true or false, the output is an actual number, like an output of a function. And so a sharp P complete problem is number set, which is like set, but now the output is not true or false, like whether it has a satisfying solution or not, but it's actually how many solutions does this Boolean formula have. Okay, like this completeness is like defined differently from a P or NP, but still in a sort of intuitive way. It has to do with this notion of Cook reduction. So but there's still sort of the most hard problems that still lie in sharp P. So any other sharp P problem can be reduced to a number set instance in a sort of nice way. So what is important is that sharp P is actually a really big complexity class, because there's this thing called Toda's theorem, and this says that the entire polynomial hierarchy, and what this is exactly is not important, but it contains P and NP, and also sort of iterated versions of NP. All of this is contained in P to the sharp P. So what this means is that if we have a Turing machine, the Turing machine, which has access to an oracle for solving number set problems, this can solve any problem in the polynomial hierarchy. So this is a really powerful class. Okay, so actually solving sharp P problems is it's just generally contains very hard problems. It also contains, for instance, strong quantum simulation or evaluating a closed tensor network. So like generally problems we don't expect to be able to do efficiently at all. Any questions about this?
Could you remind me what strong quantum simulation is?
Okay, yeah, so strong quantum simulation is where we are given a quantum circuit and we are given an input state and we are given, and then we're asked, okay, what is a probability or marginal probability of observing certain measurement outcomes? So you're sort of composing your quantum circuit with a given state and a given effect, and then you're asked for, okay, what is the amplitude of this thing? So it's exactly just tensor contraction in like a formal sense.
Thanks.
Any other questions? Okay. Yeah, so now we can formally state the main result, which is that number set Cook reduces to circuit extraction, meaning that number set is in this complexity class, where now I write FP to denote it's a functional polynomial expression, not outputting true or false, or outputting an actual like result. So if we have like a polynomial Turing machine which with access to an oracle that solves circuit extraction, then we can solve number set. Okay. A corollary of this, using Toda's theorem on the previous slide, is that if there was a polynomial time algorithm for circuit extraction, then the entire polynomial hierarchy collapses, and in particular we would get P equals NP. Okay, so it's highly unlikely that there is a polynomial time algorithm for circuit extraction. Where in circuit extraction I mean this formal definition I gave earlier, where we are just given any ZX diagram with the promise is unitary, and we know nothing else about the diagram. Okay, so let me give a sketch of the proof, because it's quite a neat argument and not so technical. So we are trying to solve a number set problem by calling an oracle that solves circuit extraction. So suppose we are given a Boolean formula. Okay, so we just have n variables and this either output 0 or 1, and we're trying to count how many times does f return 1. So how many inputs do we get 1 out? So the first step is we want to construct a ZX diagram for the linear map LF which just acts in sort of, it acts on quantum states by just applying f. Okay, so we input a computational basis state, and the output is a single qubit, which like the value of f. We can do this quite easily using ZX, because we can write this Boolean formula f as a tree of not and and operations. And of course, we can write a not as a ZX diagram. We can also write an AND gate as a ZX diagram, which is this thing. You could also use triangles or whatever favorites, or like an H-box or whatever. But this is like a way to do it in just vanilla ZX. Okay, so using this, we can write this LF as like a small ZX diagram. Small, meaning like poly size in the number of variables. And now we have like an interesting thing to note, which is if we take this diagram LF and we input like Z spiders, so this is like plus states, then really we get like a sum over all possible computational basis states, which means that we're sort of counting the number of solutions in the states, right? Because we get a 0 out if the input gives 0, and we get a 1 out if the output is 1. So here we get a superposition of 0 and 1, which is counting how many solutions we have. Okay, so A1 is sort of measuring the proportion of solutions. Now, up to normalization, we can write this state as a y rotation applied to 0. Okay, so this is not a normalized state because we're doing sort of post-selection kind of thing. But this is just a state, we can normalize it, and then it's this y rotation applied to 0. And what's important is that this rotation angle alpha is uniquely determined by the number of solutions to f. Okay, so determining the number of solutions means we just need to determine alpha. So if you can determine alpha, we are done. Okay, clear so far? Okay, so now the issue is we need to encode this into a unitary diagram, because circuit extraction only tells us stuff about unitary diagrams. So what we do is we just take the state and we use it as an input to a controlled operation in such a way that the overall diagram is unitary. Okay, so we can easily verify it's unitary. So we just take this part here, and we saw on the previous slide that this is actually the 0 state applied to this y rotation. Now, a y rotation we can write as this like S gate and S dagger gates around an X spider. And we just do some spider fusion, and we see this whole thing is just equal to an X rotation. Okay. So this diagram here, this diagram 1, is proportional to a unitary, namely just an X rotation over an angle alpha. And remember, this alpha is uniquely determined by the number of solutions to the set instance. So if we feed this diagram 1 into circuit extraction, well, it is proportional to a unitary, so we do get out a circuit. And this circuit is a 1 qubit circuit, right? Because you have a single input, single output, so a 1 qubit circuit. And this is just a list of gates, and we know this list of gates evaluates exactly to X alpha. And because it's a single qubit, we can just multiply the matrices, and then we just get the matrix out. So we just inspect it, and then we see what alpha is. Okay, so we just multiply out the gates, and then this allows us to calculate alpha. And now we have alpha, so now we know the number of solutions, so we are done. Okay, any questions about this? I mean, obviously there's like technical details that need to be worked out, but you can read the paper if you want to know those. Okay, so why does this work? Well, it's the diagram contains like a polynomial number of spiders, a polynomial number of variables of the set instance, but the circuit has exactly 1 qubit. So that means that the circuit itself is very simple, because it doesn't, the number of qubits doesn't grow with the set instance. And furthermore, like our requirement that the circuit has a polynomial number of gates in the number of spiders of the diagram, well, that means that the circuit has polynomial number of gates. And multiplying out a polynomial number of constant sign matrices, well, that takes polynomial time. So this is all fine. This all works out efficiently. And then, yeah, we also only need to know the value of alpha up to a polynomial number of bits of precision, because, well, it's like a fraction on like 1/2 to the n. So if we know n bits of precision or 2n bits of precision, we can definitely determine it up to close enough value. So all of this like works out, and it's all polynomial time, and it works out. There's an interesting relation to post-selection here, because the diagram I gave we can also present as just a post-selected circuit. up to a constant. So we have here the standard sort of classical oracle, which like calculates the value of f and then XORs it with a value here. So we can write just a post-selected circle like this, which implements the same operation. But interestingly enough, this post-selection here that we do here, we get the correct value in the measurement with a probability that's at least 1/4, and this is independent of n. So that means that the probability of observing the correct outcome, if you were to do this measurement, is bounded. So we can just do this a constant number of times and then get this thing with high probability. So we could, in fact, implement the circuit with high probability on a real quantum computer, right? So why can't we use this to solve number set on a quantum computer? Well, the adjacent possible values of alpha are actually exponentially close to each other. So to distinguish the two values, we would need to take an exponential number of samples of this thing. Okay. So if you were to do this on a quantum computer, we need to take exponential samples and then we would calculate the value. But this is, well, classically doing it also takes exponential time, so there's not really a benefit. Yeah, so running this circuit on a quantum computer doesn't give you a benefit because you need exponentially number of samples. So yeah, so the benefits, the reason our method seems to work is not because we're sort of exploiting the post-selection. It's that we're exploiting the fact that we can explicit description of this quantum circuit on just a single qubit, which allows us to exactly calculate the matrices, which allows us to inspect the unitary and determine this value to like way higher precision than you would be able to do using like this weak simulation, using just running it on a quantum computer. Yeah, just sort of an unrelated observation is that by casting post-selected circuits, viewing them as ZX diagrams, we can also view our circuit extraction result as like a statement about post-selected unitaries. So if we have a post-selected circuit where the overall linear map is still unitary, then writing this as a quantum circuit, so removing the post-selections, is sharply hard. This is like almost exactly the same problem as circuit extraction. Which, when put in this way, might not be too surprising that like a problem related to post-selection is like hard, because by Scott Aronson's result, we know that being able to sample from a post-selected quantum circuit allows you to do also hard things. But like it's different in the sense that the power does not seem to come from being able to post-select, as this like thing shows, because the correct post-selection probability is quite high. It's really just being able to inspect the circuit is what gives the power, which I think is cool. Okay, so this is sort of the vanilla circuit extraction algorithm, where we just have like we need to exactly synthesize the unitary not using ancilla, just using unitary gates. There's a couple of ways in which we can generalize it. For instance, by allowing ancilla, by using auxiliary qubits. This is exactly the same definition. The only change we make is this blue stuff. So now we allow the circuit to contain auxiliary qubit preparations, measurements, and classical corrections. But crucially, we only allow a logarithmic number of qubits, of ancilla qubits, logarithmic in the number of spirals of the diagram. And then we can use exactly the same proof, because now the number of qubits our circuit contains is logarithmic in the number of variables of the step instance, and that means we can still do sort of efficient matrix calculation. Efficient meaning polynomial time. So this problem is still sharply hard. If you allow a polynomial number of auxiliary qubits, then that's an open problem. Like we don't know if that's hard or not. At least like our method does not seem to work to prove hardness there. A different generalization is to do approximate circuit extraction. So now our input also takes a precision parameter. So we want to output a circuit that's only approximately the correct unitary. And so now we allow our diagram to increase in size in like the inverse of this error parameter, which is sort of like a standard thing to allow when you do approximate synthesis. And yeah, our unitary now is an absolute approximation for like a certain definition for absolute approximation. And just by choosing the precision parameter correctly, this is still sharply hard using almost the same argument. Like you just need to be able to approximate this value alpha closely enough. So if you just pick epsilon small enough, then it still works. And because of this dependence here, it's still a polynomial size circuit, so you can still multiply out all the matrices. Yeah. Okay, so these are all still sort of examples of going to a circuit. But as I said, the main motivation for doing circuit extraction is what you really want is you want to run the diagram on a quantum computer, right? You just want to know what happens, like if we simulate this diagram, if we actually run this unitary on a quantum computer. And a circuit is just like a sort of useful intermediary so that we can compile it to a circuit and then give the circuit to the quantum circuit, to the quantum computer, and then it runs it and we get an output. So really what we want is to sample from the unitary diagram, right? So we can just bypass circuit extraction and directly encode what we want to do. So we call this problem unitary ZX sampling. And here our input is still a ZX diagram, which is proportional to unitary U. But now our output is not a circuit. The output is just a sample, which is from the probability distribution that we would expect from this unitary, right? So the ZX diagram implements a unitary. We want to sample from this unitary, okay? Now, obviously, this problem is at least as hard as BQP, as just sampling from a quantum computation, because for a ZX diagram, we could just input a regular quantum circuit, and this would allow us to sample from the quantum circuit. So this is just doing weak quantum simulation at least. But in fact, we show it can do probably more than that. Namely, we show that NP randomly polynomially reduces to unitary ZX sampling, which means that NP is included in this complexity class of BPP with an oracle for unitary ZX sampling. So this means that with higher probability, if we have access to an oracle that gives us samples in this way, we can solve NP problems. Okay. As a corollary, this means that if there was a procedure where we can take a unitary ZX diagram and give it to some black box, which then allows it to be run on the quantum computer, then NP will be included in BQP. So in particular, like say we don't extract to a quantum circuit, but we extract to a measurement pattern, or we extract to a lattice surgery diagram, or whatever makes it run on a quantum computer. If we could do this, then NP would be a BQP, which is very unlikely. Okay, is there any questions about these definitions and this stuff? We're going to give I'm going to give a proof sketch of how this works next. Okay, then let me sketch the proof. So there is this thing called the Valiant-Vazirani theorem, and this says that to probabilistically solve set, it suffices to solve U set, which stands for unique satisfiability. So this means that we're given a Boolean formula, and we're asked if there is a solution to it or not. But we are promised that if there is a solution, the solution is unique. Okay. And the way this works is that this reduction, how this works is, if we're given a set instance, then we can do a certain procedure to it where we randomly generate a number of set instances, where with high probability, most of these will have a unique solution if there was a solution. So that being able to solve set instances with a unique solution, it gives us a way to solve the one with many solutions. So this means, like for us, it suffices to just be able to deal with these set instances that have a unique solution. So given such a Boolean formula, we construct the same diagram as before. So this diagram that implements an X alpha rotation or an identity, because if there's no solutions, it just implements identity. Or if there's a unique solution, it now implements X alpha, but crucially, we now know what this value of alpha is, because it's just the value of alpha associated to a unique solution. Okay. So now let M be just a 1 qubit matrix, which maps 0 to 0 and X alpha 0 to 1. Okay, so this is a very non-unitary matrix, because these 0 and X alpha 0 will definitely not be orthogonal, because alpha will be very small in general. But because it's a 1 qubit matrix, there's like a constant sized ZX diagram we can write down that implements this matrix. And now look at the following diagram on the left. So this bit here, just like with the red spider and the -π/2 and the LF, is the diagram we had before. So this is the part that implements this X alpha rotation. So yeah, we just write it like this. And yeah, we have this S. This S is whether F is satisfiable or not. So if S is 1, we get an X alpha rotation. If S is 0, we get an identity. And then by the property of M, we can put this together with M, and we see it becomes an S pi. Like it's either a ket 0 or there's a ket 1, depending on the value of S. And then we just do some rewriting, and we see it becomes this thing. So this diagram on the left is either implementing an identity if F is not satisfiable, or is implementing a NOT gate if F is satisfiable. So that means if we feed this diagram to our oracle for sampling from a unitary ZX diagram, that we get out 0 if it is not satisfiable, and we get out 1 if it is satisfiable, right? And if we only get a sample outcome with like just approximately correct, we just do many samples until we are like very sure of our answer, and then this allows us to approximately solve the unique set instance where we promise that it has a unique solution. And then by doing the construction from Valdian-Twatzerani, this allows us to also solve arbitrary set instances. So we can, with high probability, solve set instances. So we can solve NP-complete problems using our unitary ZX sampling problem. Okay, so conclusion, circuit abstraction is hard. Meaning, if you don't have any promise on the diagram, except that it is unitary, then this is a very hard problem. There's no efficient procedure that is going to solve it. Allowing approximate extractions or allowing sum ancillas does not make it easier. With sum, I mean a logarithmic amount. It's an open problem when it's a polynomial number of ancilla. In fact, any way to extract samples from a unitary ZX diagram is at least NP hard. Okay, we don't know if it's maybe even harder than that, but it's at least NP hard. Future work, well, what is the exact complexity of circuit extraction? We know it's at least sharply hard, but the best bound we have on it is that it is in this complexity class. So this is like the functional version of NP, and then it has access to an oracle of NP to the sharpie, which is like a really powerful oracle. So maybe there's like a better bound, but we don't know. And is circuit extraction for deterministic mesh patterns also hard? So if you imagine that you have some measurement pattern which is described by a collection of ZX diagrams that each implement the same unitary, like is writing this as a circuit also still hard? Because then there's more regularity conditions, because they are all based on measurements and corrections, and it's still deterministic. So is it still hard to make it into a circuit? We know that if that's the G-flow property, so if it is like uniformly deterministic with uniformly stepwise and strongly deterministic, then it is easy. But what if we weaken that to just determinism? Is it then hard? Yeah. Okay, that's what I want to say. So thank you for listening, and yeah, go read the paper if you want to see all the gory technical details. And thanks.